Yo, class. Today we're moving on. We've got a big topic to cover, right? The difference quotient, right? So, if you've heard anything about calculus, you've probably heard about derivatives and integrals, right? So, the difference quotient is going to set up derivatives, really, and we'll get more into that in the next video, but today we'll just introduce the difference quotient, explain what it means, and really go into depth as to what it looks like visually and analytically, right? So let us begin. It's going to be a big topic today, so put on our thinking caps right away. Okay, difference quotient. If you've ever taken like a pre-calculus class, you've probably seen this before. Essentially, it is, I'll use f of x minus the change in x. Oh, my bad, plus change in x. Minus then f of x, right? All over this delta x, right? And this delta x is going to be the change in x, right? Change in our input value. All right, so we'll go through this in a different color, right? Now we ask ourselves, what is this difference quotient describing? We have this f of x plus delta x minus f of x. That's our numerator term, right? Now, if you think about what f of x is going to give, sorry, it looks like it's pretty tough to see because of the light there. Actually, let me rewrite this just a bit lower so that you all can see that. We get f of x plus delta x minus f of x all over delta x, right? Now, okay, we have this numerator part. This delta x here, or my bad, f of x, that's just a function, right? If, let's say, let f of x equal, and then that equals some function, right? Now, this f of x plus delta x, or plus the change in x, that's what that delta indicates, right? That's if we plug in a little bit more to our function, and all that's over the change in x. So it's pretty tough to like understand what that means, so I'll draw out a graph, and I think it'll help a lot, right? Have this graph over here. Okay, a function of x, right? Now, I'll draw a pretty basic curve here. Getting at the origin? Okay, just in the first quadrant here. So, x really just describes any input value. So, I'm just going to choose right, how about here? This. Now I'll use a different color. If I were to label the ordered pair for this first point here, it would be x, f of x, right? Because we don't necessarily know what those numbers are. But we do know that if we plug in x, we will get an output value, f of x, right? Now, if I were to add, and I'll use a tertiary color here, if I were to go over a distance delta x, right, we get a new point. Now this new point would be x plus delta x, and then the y value, the output value, would be f of x plus delta x. Sorry if that's a little tough to see there, all the way out on the side. Here, I'll bring the camera in so you can see that. Those are the ordered pairs for that function. I'll set this back in its spot. Okay, now, here we have a distance between these 2 points of delta x, right? Because this ordered pair is just x plus delta x. And now, also we have a difference in y values as well. I'll just label that delta y for now, right? We have a change in y value and a change in x value. So now, I'm gonna do one last thing, and I hope it all clicks. I draw a straight line connecting these 2 points, right? Now that's not necessarily straight, but it's my best attempt, right? I draw a straight line between these 2 points. Now what our difference quotient over here is saying is this output value, right, f of x plus delta x, minus the output value of this leftmost point, right, over this difference, this x distance, right? So really what this difference quotient is giving us is a change in y value over a change in x value. It's just a nice fancy way to write it, right? Because what the difference quotient allows us to do is delta x could be anything, and f of x, we could set that at any point, right? We could set, and I'll use little red markers here, we could compare these 2 points, right? We can compare these 2 points. We can compare any of these points. And between any of them, we could draw a straight line, and our difference quotient finds the change in y over change in x. And if you've taken the pre-calculus course, or really just any algebra course, you'll recognize that's a slope. Now, calculus is all about slopes. Remember, calculus is the study of continuous change, right? How does continuous change happen? Through slope, right? Slope describes the change in a graph's output. So the difference quotient is going to find us the slope of that line that I draw between the 2 points, right? And now, why this is important is in our next video, we're going to take the limit. We're going to do a limit as that delta x approaches 0 of our difference quotient. And now as I write this out, think about what that limit is going to do. We're describing what happens to this difference quotient, the slope. What happens to a slope as the distance, the x distance here, approaches 0, right? I'll draw out another graph over here, probably in black, right? Swollen graph. How about just like a parabola, right? Now, we're taking this point here. That's going to be our x, f of x. Now, let's start off with a pretty big distance here, right? That'll be our x plus delta x and f of x plus delta x. Ooh, I'm getting pretty close to my stuff here. Sorry, it's overlapping. All right. We have a pretty large distance here. Pretty large change in x. And now look at our line, right? I'll draw it as a dotted line for now. And we have a slope. Our difference quotient will find that slope, right? That rise over run. Now what happens if I put that point here? That slope's going to be different. And now, what if I get closer, right? And now, what if I get really, really, really close? To the point where it's hard to compare, right? And as you approach 0, what you begin to see is those points almost touch, right? And the slope between them is going to be what we model as a derivative, right? The slope between x and the next infinitesimally small point over, or infinitesimally, yeah, you get it, right? As we converge those points in on each other, we're going to get a slope that we can't model a slope that small on a level this big. So we need to use a limit to show that we're getting infinitely close together with those 2 points. And we're going to use a slope to find that, or that derivative, really. We're going to use a limit. We're going to take that limit of the difference quotient. That's going to give us a derivative. And as to why we have all these fancy x and delta x terms instead of just numbers in here is because our difference quotient allows us to, again, pick any 2 points. Pick any point for our x value, allows us to pick any point for our x plus delta x point, right? And so what that's going to do is, as we approach 0, instead of getting a number like we have in the past for our limits, we're going to get an expression, a whole new function, right? And that function is going to be modeled as our derivative function. So in the next video, we'll elaborate, we'll actually do that limit, and you'll start to see some patterns with the difference quotient, right? I find the difference quotient very, very interesting because before you know it, we'll completely forget about it. We'll stop using it because we have some tricks for derivatives that'll make them a lot easier. But I always like to make that analogy between what happens as you squish those points infinitely close together, what happens to that slope, right? What we actually call it is, and that graph's really messy, I'll just draw a third one, right? Now, let's say that distance is approaching 0 and we took that limit of our difference quotient. That slope is actually going to be what we call a tangent line, right? If we were to draw a straight line between those 2 points, we'll get a tangent line, and we're finding the slope of that tangent line with derivatives. So the big topic of our next video, which will introduce derivatives and the limit definition of a derivative, that's what that difference quotient describes, is that we can find the instantaneous slope at any point. And in calculus, we can do a lot of stuff with that instantaneous slope. And as you know, there's a lot of calculus and stuff like engineering, physics, even like medicine practices, right? Calculus is in everything. We can model a lot of stuff with derivatives and calculus and all that stuff. And so kind of as my call to action to you, the audience, if you're at the point in your life where you're taking classes in school, when you go over that content, especially in like science classes like physics, chemistry, biology, start to think about the application of calculus in those, because you will look at equations, even in algebra-based courses, right? Like introductory chemistry and physics. You'll start to make connections between what we learn in the field of calculus and how that ties everything together in other subjects, right? It's very interesting. So, and we'll learn about all of that in the next video, though. Anyways, I hope you enjoyed this lesson about the difference quotient with me. As for Dude, he'll be returning soon. He has some calculus homework to do still. He'll be with us in a moment, in a few videos here. So just to recap before I tune out for this one, the difference quotient, it's describing a slope in fancy terms, right? A slope between 2 points that we really get to choose. And eventually we'll get to the point where those points that we choose are infinitely close to each other, and that's going to get us a derivative, which we'll go over in the next video. So anyways, thank you very much. Goodbye, class.